Hello everyone, this is N. Kavitha working as Assistant Professor in Department of Electronics and Instrumentation Engineering, Hindustan College of Engineering and Technology. Today we are going to see a specific topic on digital logic circuits, which is code converters. These code converters are the most essential part in digital logic circuits. Before getting into code converters, we must know what is meant by a code. Generally, any digital data can be represented, stored, and transmitted as a group of binary bits. So, this group of binary bits is called as a binary code. The binary code can be represented by a number as well as the alphanumeric letter. The codes are classified into two types. One is the weighted code, the other one is non-weighted code. First, we would like to see what is a weighted code. In weighted code, each digital portion will be having a specific weight or a value. For example, if in case of a BCD or if in a case of 8421 code, we can find that each of the binary coded division is a weighted code where each digital portion will be assigned with a specific weight. The next part is called a non-weighted code. In non-weighted code, there is no positional weight. That is, each position with the binary number is not assigned with any prefix value. No specific positions are assigned to a bit position in non-weighted codes. For example, there are many non-weighted codes like gray code, XS3 code. In this specific video, we are going to cover few code conversion topics. Before getting into the code converters, what is the main purpose of code conversion? So the code conversion is used to change the data which is present in one type of binary code to the data which is present to the another type of binary code. Some of the codes are BCD, gray code, XS3, ASCII codes and so on. The majority used code converters of conversions are binary to gray code conversion, vice versa, gray to binary code conversion, BCD to XS3 code conversion, XS3 to BCD code conversions. In this specific topic, we are going to just focus with the basic code conversions of three code converters, namely binary to gray code conversions, gray to binary code conversions, and further binary to XS3 code conversions. The very first code conversion is binary to gray code conversions. So this gray code is also a non-weighted code. As I explained earlier, these non-weighted codes, they do not possess any weight. For example, this gray codes will have a special property that any two numbers coded differs by only one bit. I'll explain you further. Say for example, if we are going to generate a 4-bit gray code, it can be calculated by the following formulas, where this G1, G2, G3, G4 will indicate the gray codes. B1, B2, B3, B4 will indicate the binary codes. So how to convert a binary code into a gray code? Each gray code can be obtained by making an XOR operation with the binary bit. Say for example, out of this 4-bit gray code, the first bit G1 will be equal to the first binary bit B1. The second data of the gray code, that is G2, can be obtained by making an XOR operation of B1 and B2. G3, that is gray code 3, can be obtained by making an XOR operation of B2 and B3. G4, the fourth gray code, can be obtained by getting the XOR of B3 and B4. I'll make the further explanations so that it is quite easy for you to understand. Let's see a 4-bit binary to gray code conversion table, which is as shown here. We know that we are going to convert the 4-bit binary number into a 4-bit gray code number, and the values of 0 is taken over here. You know the value of 0, it is going to be a 4 zeros. Since all the code values are 0, we are expecting the output as 0. When we take the second category, we are taking the value of 1. The equivalent binary value for 1 is going to be 00001. And in this case, we are going to check out the gray code conversion. As indicated earlier, this is going to be my B1, which is binary data 1, and this is going to be my B2, binary data 2, and this is going to be my binary data B3, and the last is going to be the binary data B4. And now, when we convert this as a gray code, it is quite easy for you to understand. I just put the first value 0. The first bit is 0. Followed by that, I have to make an XOR operation of the first 2 bits, which is I have to make an XOR operation of these 2 bits. You know the truth table for XOR. When both the conditions are true or when both the conditions are false, the output is going to be 0. When either one of the input is 1, the output will be 1. In this case, the first bit is 0, second bit is also 0. So when I make XOR operation between the first and second bit, the output is going to be 0. Further, I have to make an XOR operation between the second bit and third bit. Again, the second bit is 0, the third bit is 0. Obviously, the output is 0. In fourth case, I have to make an XOR between the third bit and fourth bit, where my third bit is 0, and when I make an XOR operation with the fourth bit 1, 0 XOR 1 is going to be 1, and that is my fourth gray code. Hope the concept is clear. So this is a way you can get a table for a conversion of 4-bit binary code to gray code. Let's look at the other example at the middle of the table. I would like to take the value 0110. As indicated earlier, I would like to keep the first bit as the same because G1 is going to be equal to B1. So here the B1 value is 0, G1 is 0. For obtaining this G2, I have to make an XOR operation of the first bit and second bit, that is 0 XOR 1. When I make XOR of 0 XOR 1, the output is going to be 1. Further, for obtaining G3, I have to XOR B2 and B3, where B2 value is 1, B3 value is 1. So 1 XOR 1 is going to be 0. Hope the concept is clear. Finally, to obtain the gray code G4, I have to make an XOR operation of B3 and B4, where my B3 value is 1 and B4 value is 0. 1 XOR 0 would be 1. So this is the way you can obtain the code conversion table. In this video, I'm just covering you only the code conversion techniques. With the help of these code conversion table, you can make a minimization using a K-map and you can arrive at a logic diagram. The next part is the vice versa. Initially, we have converted the binary code into a gray code, and here we are going to make the reverse operation where I'm going to convert my gray code into a binary code. Again, you know what do you mean by a gray code and what is a binary code. Here the formula is quite different. Here the input is going to be the gray code and the output is going to be the binary code. As indicated earlier, B1, B2, B3, B4 are the binary codes. G1, G2, G3, G4 are the gray codes. Here the formula is quite different, where B1 is equal to the G1, B2 equal to the gray code at position 2, G2 XOR B1. That is, we are going to make an XOR operation of the second bit of the gray code and first bit of the binary code. Followed by that, we have got B3. B3 can be obtained by making an XOR operation of the third gray code with the second binary code, and finally B4 can be obtained by making an XOR operation of the fourth bit of the gray code along with the third bit of the binary code. I would like to make it simple by giving you an explanation of this specific conversion table. Here we are just going to take out the gray code, and these gray codes are being converted into a binary code. When we consider the very first bit, we could like to see that the first bit will be having the 4-bit gray codes. As I told you earlier, we are just seeing the conversion of 4-bit codes. Either the 4-bit binary code can be converted into a gray code, or the 4-bit gray code can be converted into a binary code. The first value is going to be 0 in all cases. So obviously the output is also going to be 0. When you take the second input conditions, that is, I'm taking a value of the gray code 0001. In this case, we would see how to convert this gray code into a binary code. Very simple. Initially, I am taking the first code as the same because the first bit is going to be 0. In this case, it is going to be quite different from the earlier case where I'm going to make an XOR operation of the second bit along with the output of the first bit. So 0 XOR 0 is again going to be 0. In next case, I'm going to make an XOR operation of the third bit with the resultant. Again 0 XOR 0 is going to be 0. In next case, I am going to make an XOR of the fourth bit along with the third bit. 0 XOR 1 is 1. So the output is going to be 0001. Hope the concept is clear to you. Here we are making a quite change in the code conversions. I would like to make it simple. We can see the other example so that it is quite easy for you to understand like how the gray code is converted into a binary code. Yes. So let's look up with the third input 0011. So this is going to be my gray code 0011. We will check out the output. The first bit is I'm going to take it same because the formula is B1 is equal to G1. So next we are going to make an XOR operation of the second bit with the resultant bit. So 0 XOR 0 is going to become 0 obviously. Next, I am going to make XOR operation of the third bit along with this result. So 0 XOR 1 is going to be 1. Now, I'm going to make XOR operation of the fourth bit with the resultant bit, and now 1 XOR 1 is 0. Now the result is 0 0 1 0. That is your equivalent binary code for the given gray code. Hope this concept is clear to you. When you convert a gray code to a binary code, you have to change the formula little bit. Similarly, you can proceed with all the other cases of your inputs for the conversion. The third type of code converter which we are going to focus now is BCD2XS3 code. As I told you already, all these codes are covering under a non-weighted code. The name itself indicates XS3 code, which means whenever you find the decimal equivalent of any given number for any BCD number, you are going to obtain a XS3 code, right? So what is the word XS3 code indicates? For each code, you are going to add an excess of 3 equivalent codes. I'll make you simple. Here, to represent the BCD, I have used the variables B0, B1, B2, B3. To represent the excess codes, I use E0, E1, E2 and E3. And obviously, E0 will represent the least significant bit, E3 will represent the most significant bit. Here comes the tabulation of how to make a conversion of BCD to XS3 code. It is quite simple. You know already that a binary coded decimal number will have 9 values. That is, the decimal ranges from 0 to 9. It is very simple when compared to the previous two codes. Here, you can take the first bit 0. The equivalent binary value of 0 is 4 zeros, right? So as I told you already, to convert the BCD number to a XS3 code number, we are supposed to add XS3 to the given BCD number. So now you know the value of 3. The value of 3 is 0, 0, 1, 1, right? So when you add these values, you will get 0, 0, 1, 1. So that is your conversion. So to convert any kind of BCD number to XS3 code number, the concept is quite simple. You're just going to add the value 3 to the given BCD number. Let's go up with the second number so that this is quite clear to you. Let's take the second input. The second input is I'm taking a value which is equivalent to 1, that is 0001. So this is the code which is equivalent to the decimal 1. As I told you, to convert this BCD number to a XS3 code number, I have to add 3 along with this number. And you know already the value of 3 is 0011. When you make binary addition to this, you know the binary addition 1 plus 1, we get some 0 and we'll get the carry 1, right? So along with this carry, what we are going to do is I'm going to put up the carry over here. Again, 1 plus 1 is going to be some 0. The carry 1 is transferred here. Again, 1 plus 0 is going to be 1. 0 plus 0 is going to be 0. So, the equivalent access code for the value 0001 is 0100. Hope the concept is clear to you. With this, I conclude the code conversion topics. With this code conversion table, you can process further. You can make the help of a K-map for minimization. For all the outputs, you can come for the arrival of your Boolean expression. With the help of those Boolean expressions, you can able to create a digital logic. Hope this video is helpful to you. Thank you.